Hello everyone. So welcome to this week seven's workshop of AI Club. And uh, so today I'll be going over the topic exploratory data analysis. I'll go through a presentation first, explaining. It will be a short presentation, and then we'll start uh, on a practical. Basically, we'll work on a notebook, and so yeah, let's begin. Let me just share my screen first. Okay, is this visible?
Yes.
Okay, all right. One second. Okay, so as you can see, our workshop is on exploratory data analysis. Now, what exactly is exploratory data analysis or EDA? So, yeah, as the name suggests, we are analyzing the data sets. And basically, whenever we are assigned with a new problem, the first thing we would want to do is uh, get the main characteristics of the data, summarize the data in visual format so that it's easier for us to understand. Uh, and we can try to gain more information on what the data can tell us, basically. Okay. Uh, so, so, so EDA for structured data basically includes univariate analysis, bivariate analysis, and multivariate analysis. We'll go through each one by one. So univariate analysis basically means we're analyzing one variable at a time. So we'll have multiple features, right? And we'll basically analyze the target feature with respect to the. We'll basically analyze one feature at a time, right? So we'll have the histograms or box plots basically. So histogram is a, as we all know, it's a frequency distribution, and it helps us really get a sense of which values of the data have high frequency, and we get a easy way to view the distribution. And as for the box plot, well, box plot again is very interesting. We can gain several uh, information just from a single figure, right? Let's say we look at this. So the first, yeah, so this middle line, right? Uh, I guess you can see here, this one, that's the median. And then we have the lower quartile on this side and the upper quartile on this side. And these ends are whiskers. So they don't mark the endpoints technically. They are not at the edge basically. They are basically at the 1.5 quartiles from the median. And so basically these points at the end, these dots that we see at the end, they are outliers basically. So a box plot, as we can see, we got so much information just from one single plot, and that's the beauty of box plot. Next, we move on to bivariate analysis. Now, there it depends on uh, what type of data we have specifically for bivariate analysis. So depending on whether the data is whether we have continuous data or we have categorical data, we'd use different types of plots. So scatter plots would be generally used for continuous data, and bar graph or bar plot will be used for categorical data. Line plot is also one way of representing data, but I would actually prefer scatter plots because we can plot the a given feature against the target feature, and we can get a sense of how one particular feature affects the target feature. So that way it's bivariate because we are using two variables. One is one feature that we are considering currently, and another one is the target feature. So yeah, so that's bivariate analysis. We can also have box plots again, but this time we can categorize them. Basically, let's say we have a categorical input and we have an output that is continuous. So we'd want to sort of gauge how the each category of the categorical input affects the distribution of the target output, let's say. So that way we can use box plots and again violin plots. Violin plot is basically uh, uh, a mixture of box plot and KDE plot. So we'll go over through them in the next slides. Yeah. So as we can see here on the left side, we have the scatter plot. It is it really helps us understand how the input feature, which is the product weight, is affecting the target, which is the product supermarket sales, right? And it gives us a very important point. So the product weights at these particular points, they have a few outliers for the supermarket sales, and we can see them here that they are not within this sort of cluster, and they are. So yeah, so we can gauge some information from scatter plots. It's not enough though, and we'll see how we can try to gain more information from these. Next is the bar plot. This is pretty obvious. So this basically gives us the count, right? Like how much is the frequency of each variable, each category of the variable. Okay, moving on. Yeah, so this is a violin plot, and it might seem a little bit intimidating at first, but it's really powerful tool to gain a lot of information from from the data in just a single plot, right? So if we look at this, as I said earlier, that violin plots have uh, the box plot and also a KDE plot, right? So this part right here, we can see this is the box plot and this is the distribution, this one, the colored one. So yeah, so we can easily see, we can see the median, we can see the quartiles and the, so these are basically the whiskers that were there in the earlier slides. And we can also this this scale of the area, this right here, this width, basically tells us the total count. So uh, what we couldn't gauge from the earlier slides was that we couldn't get for each category, we couldn't get how the supermarket sales are affected, right? In the box plot we couldn't gain any of those sorry, in the bar plot we couldn't get any of those characteristics, but here we can easily see. So this width basically gives us the frequency of the low fat. So as we can see, low fat is of the highest frequency, normal fat is lesser, and ultra low fat is very less frequency. And so these are basically the categories of this particular feature, product fat content. Okay, now coming back here. So yeah, the violin plot can give us a lot of information, especially because of the width and the height, and how each category has a distribution for the target output. So this is the target output, product supermarket sales. That's our target. Okay, moving on. So yeah, we can use a multivariate analysis, and let me show you. The correlation heat maps and the pair plots are the two most important. So So as for the correlation heat map, so they basically what we do is we for each feature, each numerical feature, we calculate our for each pair of numerical features, we calculate the correlation between them, and then we can sort of produce a heat map. Now, in this heat map, uh, a correlation of one means they are very highly correlated. Correlation of -1 would imply that they have very high negative correlation, right? And the correlation of a smaller value, either positive or negative, would mean that they are not really related. So, so from this particular heat map, we can see that the basically the darker ones would imply that they are negatively correlated, and the very faint light ones would imply that they are positively correlated. So we can see that this these two features are actually this old peak and this slope. These two features, we can see that they have a high negative correlation, and it is apparently the highest. And other than that, there isn't much correlation between any other pairs of variables, right? Okay, so moving on. Yeah, so this is a pair plot. We can use a Seaborn for a pair plot, and what this basically does is we get the histograms on the diagonal axis. So these are the distribution frequency distributions, and we get the scatter plot on the rest of the plot, right? Okay, and this basically helps us understand the relationship between two or more variables. So, for example, in this one, we have age versus old peak, right? So, so, so we can see how they're distributed, and the colors. These colors, the orange and the blue, are for the target. So basically, I've separated those according to the target, and yeah, so we can see that in this graph, especially, they are somewhat separable, and even this one, they're actually symmetric graphs, but so yeah, so we can try to find some similarities, or we can try to find whether the data is separable, or we can gauge more information from these visualizations basically. Now, for the text data, we don't have text data in our practical notebook that we'll be going through, but let me just go over some of the analysis used for textual data analysis. Now, so we can use word clouds. They basically map the word frequency, and each word is, you must have heard them before. It's very common even outside of data science. So yeah, so this is a word cloud. We can see the largest one is basically the most the one word that appears most frequently, and the size basically defines how frequently they appear, right? Okay. And also collocation and concordance. There are a few ways that textual data can be analyzed. Collocation basically means that we uh, pair two or more groups of words together, and we can see basically how a particular word uh, is basically how a particular word co-occurs with which another words basically. And as for uh, concordance, it's sort of a similar concept. It tries to capture the context uh, of the word. So yeah, so these are some of the uh, techniques for analyzing the textual data. Now let's move on to feature engineering. So basically, why we perform exploratory data analysis is to get an idea of how the data is distributed, but it is also important that we generate new features, uh, or we basically engineer the current features so that our model can be trained in a better way. So, for example, uh, we would basically have different types of feature engineering techniques, and some of them are creating new features or transformation. But feature engineering is very, very essential if you want a model to learn very quickly and learn effectively. Basically, we want the learning process to be smooth, right? So that's why feature engineering is very important. So yeah, as I said, so we could have new feature creations, or we could have feature transformations, and then encoding and scaling, right? So what do I mean by creating new features? So so I basically uh, you can have, let's say your data contains sequential data with separated day wise, right? So you could have uh, trends to be different for day of the week, and let's say on the Saturday, Sunday, on the weekend days, basically the trend is really different. So what we could do in that case, or in a similar case, is we could have a new feature that just says that is binary, and that just says whether or not that particular day is a weekday or a weekend, right? So so that's just one example of creating new features from the existing features. As for the feature transformations, this slide is does a really good job at explaining that. So let's see. Uh, yeah. So the if we plot our data, let's say in Cartesian coordinates, and let's say the distribution in is such that the polar coordinates would make it really better, and see, as we can see from here that this we have transformed the coordinates from uh, x and y to polar coordinates, right? So uh, yeah, so that is feature transformation basically. And another one is there are some mathematical transformations that we can apply, such as we can apply uh, log transformations, or square root transformations, or square transformations, or cube root transformations, right? So basically, why do we apply feature transformation in the first place for continuous data, let's say? So this is a product shelf visibility. This is a continuous data. Now, as we can see here, this data is skewed. What I mean by that is its tail, this end, is on to the right side, right? It has a tail onto the right side. That means that it's skewed to the right. Basically, we don't want our data to have a left skew or right skew. We want the data to be as close to be a Gaussian distribution or a normal distribution as possible. So we would perform several transformations. So in this case, let's say our data is skewed to the right. So what we can do is, in this case, we could perform the square root transformation and sort of get a bit more cleaner, uh, get it more cleaner. See, this is not as skewed as this one is, the transformation, and it's more closer to a Gaussian distribution, right? Okay, so uh, moving on. Uh, yeah, so the textual feature engineering. So we could have so the simplest example for text feature engineering is the bag of words model. So given any group of words, we could just uh, sort of bag each word into according to its frequency, right? And we could just have that as one feature. And even though it seems very simple, and it seems like it is so simple that it shouldn't work, but yeah, even a bag of word model, which is a unigrams model, even that works out to be pretty well, and even that gives good features. And we could also try some other types of feature engineering, such as generating n-grams and generating part of speech tokens. So yeah, these are basically examples of feature engineering for texture data. And of course, you guys already must be knowing this. You must have used this encoding the data, right? So this is less of a feature engineering and more of a data cleaning technique. So we basically want the categorical variables to be encoded, either label encoded or one hot encoded. So whenever the categorical uh, variables, they have categories, and basically those categories have an order, or basically say that it's an ordinal categorical data, right? So in that case, we'd use label encoding, and in other cases, we'd use one hot encoding. And so yeah, moving on. We would for the numerical features, we would have scaling and normalization. So z-score normalization, which is right here, this is most common normalization technique used. Even for batch normalization in neural networks, this is still used. Another one is L2 normalization. And so yeah, another one is also min-max scaling, which is right here. So we could use pre-trained libraries provided by sklearn or other libraries to do these things. And we are basically trying to uh, sort of make the learning more smoother, right? Uh, because when we scale and when we normalize the data, we'd basically have the each variable, so each feature would be in smaller ranges, and that would help in smoothing the gradient descent process. Okay, so yeah, that is all for the PPT, and let's move on to the cool stuff. We basically be working on a notebook, and I'll be going through it, and then I have other notebook created for you guys, and you guys can work on that as well. So that way, yeah. Okay. Let me just share the one sec. Okay. Let me share the details for the drive. Sorry. Okay. So these are the links. Now, what I want you guys to do is uh, basically go to this drive link, and and add it to your drive. So you would have a shortcut like add to my drive shortcut or something like that. And yeah, just add the folder EDA to your drive. Let me do it along with you guys. One second. I'll just share my screen real quick. Yeah. Okay. So, uh, yes, this drive link, what we want is, I want you to guys to go to the EDA folder and add it to, there'll be a shortcut that says add it to my drive. So your my drive should have an EDA folder like this. This is basically would help us for the workshop part, for the practical notebook thing that we will be going through. Let me know if anyone is having any problem with this. Okay, I guess everybody has opened the links. Yeah. As for the other three notebooks, okay. Uh, let's just first start with the supermarket regression. This notebook. This is actually from Kaggle competition and a tutorial that I found, and I played around with it basically, and for the competition also. So let's let's see our uh, EDA in action basically. You can run these cells along with me, but for this notebook, it's really not that required. For the next one, uh, it will be required basically because I would want you guys to perform the EDA process. One second. I don't know why this is taking so long. Just yeah, that's the issue with using collab. It's just not quite reliable, I guess. Yeah, I guess it should work now. Okay, So if you guys are running it along with me, then I would suggest creating copies of the notebook in your own drive and work on those rather than uh, so that can cause some problems in Google Colab, right? So we could just have this option, save a copy, and so that way you can have a sort of code along, right? And okay, so this CSV file is right there that contains a data set. Okay, yeah. So there are like 5,000 or something rows and 13 features. Uh, yeah, so as you can see, we cannot really gauge any information just by looking at the data set, right? That's why we'll be doing the whole EDA process. So okay, we'll go through everything step by step. So this yeah. So I just have this describe method being called on the data, and it gives us a lot of information already. We know the mean, standard deviation, and minimum, maximum for each numerical feature only, right? So this is just for numerical features, and yeah, so this is quite good. So, but we want to see the actual distribution of each variable, so that we can do. We'll see how to do that. Yeah, again, I'm removing these few features that are not really important. They're basically identifiers, right? So uh, having identifiers can be really, it can cause the data to have multiple categories, and it can cause the data to be really, really large. So instead of having an identifier and encoding them, it's best to simply just drop them most of the time. So that's what we'll be going through here. Now, uh, what I've done here is I've basically divided the features into numerical and categorical. So as we can see, the describe gave us information on the numerical features, and I've grouped them here, and the rest of the features are basically categorical features. And product supermarket sales, that is a target variable, that is something we need to predict, right? So the problem itself is, given these features of the product, uh, just predict the supermarket sales. It's the sales of the product, right? Okay, moving on. So yeah, what we can use for univariate analysis here is a box plot, because like I said earlier, just by a single plot we can get a lot of information from because of the box plot. And so yeah, so basically in EDA what is important is we would want to get a sense of what our data, how our data is distributed, and uh, we'd also want to sort of get ideas for the feature engineering process. So we'd get to that in a minute. Okay. So yeah, these are the box plot. As I mentioned earlier, these are the whiskers, and these are the outlier points. Those points are basically outside of 1.5 quartiles. So one quartile would contain. So this is the lower quartile and this is the upper quartile. So they would contain 25% of the data set of the data. Okay. And okay, so as you can see that production visibility has quite a lot of outliers. Other features don't have outliers other than this one, which is our target output. Anyways, moving on. This was one way to represent the numerical features. Another way is we could plot the numerical features versus the target output, and we can get a sense of how the feature is how the feature is influencing the target output. So that's what I've done here. Okay, so the first graph really is not that helpful. The second one, we can see that there's a little bit of outliers here. So these values might be of interest. Okay, and this is for the price. Okay, as we can see that there is a sort of a correlation between product price and supermarket sales, that in general, not always, but in general, it is that as the product price increases, we see higher sales. Although there are a lot of noise, or not noise, but the data that doesn't really fit into that correlation right here, as we can see. Okay, moving on. Uh, yeah. So as for the categorical features, so I also added the opening year, which is the numerical feature in here, because it just made more sense to do add it here, because it's basically yearly distributed, year wise distributed. So it has discrete values for each year. So, anyways, for the categorical columns, we have the bar plot, as I mentioned earlier. So, yeah, this gives us basically frequency of each category. So we can see that these categories have really high frequency, and these don't have as much frequency. Even actually, we had gone through this example, I think, in the PPT, that low fat, sorry, low fat is the highest and ultra low fat has the lowest frequency. Anyways, moving on. So yeah, these are basically ways to perform univariate analysis on the categorical features. Now, let's move on to the bivariate analysis for the categorical features. Here, basically, as I mentioned earlier, we'll be using violin plots because we can just get a lot of information from a single plot in the violin plot. Okay, so as you can see here, this is really important. What I've written here, so I've scaled them by the count, which means that this width represents their frequency. So we can see that the 5,000 is the roughly the mean for the low fat, and roughly the median for the low fat category, and this width is really high here. So that what it means is uh, there are a lot of examples that have low fat at this value, and the supermarket sales at this 5,000 value basically. And so yeah, so we can see the median and the whiskers. These are basically box plot for the supermarket sales, but we have categorized it per each category basically. So yeah, uh, we can really glean a lot of information. So as you could see earlier, we could see that the ultra low fat, it has low frequency, and even the variance is quite low for uh, the supermarket sales. Anyways, what basically we can try to glean information from these plots is we can try to sort of get those categories which are kind of dominant. Like we can see this category, or you can see but it's fruits and vegetables, that category, and snack foods, that category. So these two categories and this one, those three are quite dominant, and so yeah, so that is an interesting finding. We could do this for all such categorical features. Anyways, moving on. So as I mentioned earlier, we could have a correlation heap for multivariate analysis. So what this basically helps us is we can easily gain information on how one particular feature is affecting another particular feature. So these type of uh, information is this type of information is basically very useful for let's say not just for machine learning models but also for business analytics or decision making from data analysis or stuff like that. Anyways, as you can see here that this particular category, this particular feature, product price is very strongly affecting target variable. So that is an interesting find, and that intuitively does make sense. Like, so the product price, higher the product price, more the sale would be. So yeah. Uh, Now for the really interesting part here. So now we're moving on to the pair plot. Now I'm using Seaborn for plotting basically, and pair plot is a very powerful tool for data visualization here. What it basically does is I have mentioned the numerical columns, so the numerical categories here, and for each numerical category, I am uh, so the pair plot will basically plot the numerical categories, and what we can do here is we can provide a hue, and using this, what we can do is for every numerical feature, we can have the bivariate analysis of that with every other numerical feature, keeping this particular column as the separation basically. So these colors that we see, they are each categorical values category. So this low fat, ultra low fat, normal fat, right? So we have separated them by the category. Okay, yeah. So each each plot here basically is like a bivariate analysis, right? So as for this particular one, with respect to product fat content, we cannot really gain a lot of information here because one particular category is dominating others. Okay, so moving on. Yeah, so even here, what you can see is we have this these colors that are dominating. So let's say household, health and hygiene, soft drinks, and others. So these products are being dominated, right? So one example of how we could do feature engineering here is we could basically have those manually clustered into one. So we basically have, let's say if I am clustering soft drinks and health and hygiene and household. So I just have a simple binary feature that says whether or not they belong into that category. One for that and zero for that. What intuition I'm basically trying to gain here is uh, the model would eventually won't give as much importance to other uh, to other categories, and we don't really want that. We don't want the model to just focus on these dominant categories. So yeah, we could have another feature that just sort of clusters them, and that's an example of feature engineering. We'll go through that now. Yeah, for the this is for the location one. uh, Actually, we can see here that some of them can separate the location actually quite well. So if you can see product price versus the sales, so this graph actually can separate the location type quite well. And so yeah, basically we can gain that information just by looking at the pair plot, right? Now finally for the supermarket type. Okay. Yeah, we have these. Again, we can see that the types are also in this particular graph: product price versus product shelf visibility. This one, that they're sort of separable, and in fact, here they are actually quite separable. They look at least appear to be. Anyway, so we can, yeah, gain a lot of information even from the histograms on this diagonals. We can gain information, like we can see that there's apparently a gap in this feature which is opening here, right? You can see there's a sort of a gap. So we could what we could do is sort of suggest a new feature that just says whether or not it's behind this gap, or so this gap is basically 2000. So whether or not it's less than 2000 or whether or not it's greater than 2000. So that could also be interesting feature. And yeah, uh, one more thing to point out, as we can see in the supermarket sales, this particular graph, actually any particular histogram we can see here, supermarket sales histogram, that this data is skewed, right? This data isn't, it is skewed to the right, just tail to the right basically. So that is not a good for prediction. So what we could do is we could apply some transforms to make it less skewed, basically as close to normal as possible. I believe even this product shelf visibility also has a skew. It's quite visible here. Yeah, it has a skew here. So even we could transform that. Other features that are sort of close to a normal distribution, we don't really want to transform them, because transformation is basically we we are making changes, we are applying some function to the feature, and that can mm, sometimes negatively affect. So we don't really want to transform if it's not necessary. Anyways, so yeah, so like it's said here, what we could do is we could try to train a simple linear regression model without any feature engineering. So what I just gave the ideas for, they were what we went through. They were ideas for feature engineering. We could just simply uh, encode the data and fill in the missing values and then simply train on it. So I'm going to do that. Okay, yeah. So it has null values, as we could see earlier. The product weight has null values. So we'll fill up the null. So this is one of the techniques to clean the data, is filling up the null values with the mean, as you can see here. And there are other techniques, like we could simply delete the rows, or we could simply delete a particular column. Anyways, moving on. Yeah, so what I'm doing is using a simple linear regression model from sklearn, and we could try some complicated models, but just for the sake of this tutorial, I'm just using simple linear regression model. So yeah, as you can see, we are getting a very high mean absolute error score, and that's not good. So we basically hope that after all the feature engineering and transforms, we would have a good enough uh, MAE score basically. So let's go through one by one. So like I had mentioned earlier, uh, we could have uh, separate the opening year. Like there's a clear gap here, right here. So this point is 1996, right? Okay, and so we could separate it by that gap, and so we have generated a new feature basically that says whether or not it was open, whether or not this value is less than 1996 basically. So yeah, another important thing is that as I had mentioned earlier, so the health, hygiene, and household, these these category and others, these categories are dominating the distribution, as we could see here. There's a lot of pink because of these three values. So what I'm going to do is basically I'm going to create a new feature that doesn't have these values basically, and as a cluster. So yeah, so that feature basically is like manually clustering into two categories. So yeah, we do that. Now for the really cool stuff. So like I mentioned earlier, this product supermarket sales, the target output, it had a skew basically, and we want to remove the skew. So what I've done here is I've applied a logarithmic transformation here. So that is uh, so yeah. So logarithmic transformation is basically I'm hoping that it will, yeah. So we can see uh, it is not so it still has a skew basically, but it's it looks a little bit better as compared to the earlier one, since the earlier one basically had a lot of values closer to the zero, and now we have transformed it to using the log function. So yeah, that is a little bit better. So I'm going to keep this. And another one was product shelf visibility, even that had a skew. So I'm going to apply a square root transformation function. So it's not perfectly Gaussian here, or perfectly normally distributed, but it is much better than this one, I believe. So let's stick with this one. And we could do the same thing again. We could remove the null values and uh, fill the null values and train again, train on the same classifier again. So what I've done here again is I've used scaling now. So it's basically robust scaling is a variation of min-max scaling that we had covered in the PPT. So that's what we are going to use. So yeah, as you can see here, the MA score is really much better as compared to like it was in the range of thousands before, and now it's really better. And we are just using a linear regression, simple linear regression classifier, and we could get a very good score just by because of the feature engineering. Right? Actually, we could train more complicated models on this, like neural networks or something like that. But in fact, even in linear regression can work really well if feature engineering is done properly. So yeah, so actually we don't have a lot of time, but uh, I guess we could have this UCI heart disease notebook that I've basically provided in the chat. And I, I basically want you guys to sort of go through the notebook, and basically what we did in the first notebook, you guys could do in this notebook, and try to come up with different feature transformations or new feature generations, or basically other types of feature engineering. So I've written some starter code. We could go through that, and then it would be great if actually I wanted to make this sort of an interactive session, but I guess there wasn't enough time that we could cover this in. Anyways, so yeah, let me. Okay, so yeah, so in this notebook, particular notebook, we have the problem of predicting heart disease. The target is 0 or 1, like that represents when for the target being true and zero. And yeah, we have several of these features, and so yeah, some are these features are numerical features, and there are other features that are some of these are categorical features. Anyways, so I've separated them into categorical, numerical, ordinal, and binary. So yeah, so this is basically similar to what we did in the previous notebook, but this time I want you guys to sort of uh, use this EDA for feature engineering. Basically, you guys can try like right now or maybe later, because this I'll keep this link open, this sharing, and you could try stuff. Okay, so yeah, so we are again going to perform the univariate and bivariate analysis on the same data, and this is the pair plot again for the numerical features. So we will have a sort of look and try to uh, get some information like this. Cholesterol, basically this column that has a little bit of skew to the right, we can see here. Even this column has a skew. So yeah, so we could, even this has a skew to the left actually, and there seems to be some relation between this stressed BPS and OP. These two is sort of separated the data. So these are some of the information that we can glean on, and this is again a frequency plot, a count plot basically, and a heat map. So yeah, so what I want you guys to do now is sort of come up with transformation ideas. I've written the transformations right here, and you could kind of go through them right now and try to perform the feature transformations, or creating any new features that you feel are would help in the modeling process, like we did in the previous notebook. So yeah, that would be an interesting thing to work on. So I've worked on starter code for this one feature, and you could try for other features if you're following along. I would really encourage you to follow along and sort of try for other features basically. And if anyone has any question or anything interesting they have to say about the data, or any any feature transformation that I could apply, or any suggestions they have, they could simply unmute themselves and that will work. Oh, I'm sorry. I didn't see the chat earlier. Okay. Oh, shit. I think the drive link is shared that way. Okay. I'll just change the.
You can't share it to other people from your side.
I'll
Because
just keep this sharing on just for the sake of this workshop, and later on I'll take this down.
share it to
But I request you guys, please don't share this particular link with anyone outside of UCI. I'm sorry, whoever mentioned themselves in the chat. Okay, okay, yeah. But I'll close down that link. So, so yeah, later. But at least for the sake of the workshop, I'm keeping it open to everyone, basically. Yeah, and if anyone has any suggestions with respect to the transforms that can be done here. So here I've tried with this cube root transform. I've tried with a few other transforms too, and this seems to be the working best. There are other features also that could use feature transformations. Or so let me just go ahead and like this particular feature, even that could have a feature transformation. Let's try that. If you guys have any suggestions or you feel any particular feature engineering technique would work best here, then please feel free to just unmute yourself and just go ahead or even enter it in the chat. I'm sorry I didn't read the chat earlier, but anyways, let's try a few things like, and then we'll apply the. So this particular one has a left skew, right? So we could use a squaring or cubing the transformation that could work here. Okay. So yeah, the data is it's a little bit better, I guess. Yeah, and we could also have we could basically try out several other transforms to see how that works, right? So yeah, this is much more Gaussian. This doesn't have any skew basically, and there are other feature engineering techniques that we could try. So like I said earlier, if anyone has any suggestions or if they are trying out anything, then you can just go ahead and speak up. But yeah. So another thing to notice here that this particular category, this particular feature, old peak, yeah. So these values are quite close to zero in some of the examples, and so what that basically is that, as we did earlier, that sometimes that can sort of dominate the this particular category being closer to a zero can dominate a particular uh, part of the model basically. So yeah, so we don't want that particular features, that particular range to be dominating. So we could even have another feature that just says whether or not that value is within 0 to 1 or 0 to half, something like that, very small basically. So yeah, uh, Yeah, so here we can see that the values are mostly zero. So we could even have this equal to zero, and we could sort of have another feature that says, like we basically did in this previous notebook, we could engineer another feature, uh, like that would just, yeah. So these are some of the tricks, some of the things that we can do for feature transformation. Basically, what my point is, we don't want any particular range of that feature to be dominating in the model. Otherwise, the model won't learn for when that value is ranging in other ranges. Basically, that feature is ranging in other ranges. So for non-zero values, I've made another feature. So yeah, so these are some of the things, some of the uh, techniques for feature transformation that we can use. Uh, yeah, and so I guess that's it. Uh, you could we could I really encourage you guys to try out some other techniques and try to get a better accuracy. I've actually not written the regression code here, the classifiers code here, but you could try uh, as we did for the similarly for the previous notebook. And I did try to get accuracy, and I was able to get roughly uh, 83% classification accuracy, I think. So yeah, you could probably try to get more than that, and feature engineering is there to help. So yeah, so this was the
Nice.
workshop on EDA and feature engineering. Uh,
That,
Renuka, do you have anything
yeah,
to say?
yeah, yeah. No, I was just gonna say that like that's a pretty good score to get started with. Like, I think there's a lot of potential as to like feature transform, and then you could probably get up like more than 83%. But like the fact that you have that already is just like I think it's a good number. But I mean, I don't have any suggestions at the top of my head, but I think overall, like this workshop was really good. Like, um, I know that they go over like in the stats classes at UCI, they go over this kind of stuff, but like the workshop really just summed up the entire series.
Yeah, exactly.
So yeah,
I
it
didn't want
was it
to
was
get
really good. Thank you
into
so much.
too much of the math. So yeah, just to give an overview without the too much of the math. So
Mhm.
yeah, hopefully this helped you guys, and thank you for attending the workshop. If anyone has any doubts or anything, then we will be sharing the recording link on the AI Club's channel page. So be on the lookout for that. And yeah, I guess thank you for attending.
Thank you. Thank you. Goodbye.